revise the topic and the tutorial sheet questions. The first one is saying what so the question is saying what factors determine the what are the factors that determine an effective collision? Now in chemical kinetics we just want to understand how fast a chemical reaction is moving, right? Just that. How fast or slow a chemical reaction is moving. That's what we discuss in chemical kinetics. Now, for a reaction first to happen itself, because how do you start talking about how fast a reaction is going to happen if it hasn't happened already? So, the first thing is the reaction has to happen. Now, look at this. Let's say, for example, you have got, uh, I can use chloride. That's okay, isn't it? Yes, I can use sodium chloride. I'll write it like this. And then let's say this guy is reacting with, let's say, potassium. Okay. Now, as you can see in sodium chloride, sodium is positive, chlorine is negative, and then potassium is a positive guy. So what happens that for this reaction to happen, potassium should never be this side. It should never attack sodium. The thing is that if it does that, this reaction can never happen. Why? Potassium and sodium are both positively charged. So we call this as a wrong molecular orientation. The right molecular orientation is that the potassium should be next to the chlorine because they are opposite charges. So one thing that necessitates that a reaction is going to happen is the correct molecular orientation. It's not the only factor. So we can write all these using what we call the Arrhenius equation. Arrhenius equation tells us the factors. The Arrhenius equation is going to give us the factors that are going to be very important for a reaction to happen. So the Arrhenius equation is K is equal to Zp multiplied by E to the power negative activation energy divided by RT. It's not a complex equation, it's something that you can know, right? So what does each one of these guys mean? They're asking that our microphones can be off, right? So that we can all get. Okay. So K, the K that we can see here is the rate constant, and then Z that you can see there is known as the collision frequency, and then the P is known as the steric factor, and then when you check on top, we have got that things there. So on top we have got this guy EA. So that's known as activation energy. And then we also have temperature and the universal gas constant R. So what do I need you to understand here? So the first thing I want you to understand is that ZP gives you something that we call A. Now what is A? A is known, okay, so A has got again another term. It is a product of these two things and I'm going to mention it. The first thing that you need to know is Z. What is Z? The collision frequency. Collision frequency is just telling you the total number of collisions happening per second. Okay? What is collision frequency? Collisions per second. Now, a reaction won't happen if the molecules that are supposed to react are not colliding. The only thing that is going to cause the reaction to happen is that the molecule should be able to collide. That is why we increase the concentration. Because when you increase the concentration, it increases the chances that molecules are going to collide. And then what is steric factor? The steric factor is a fraction of molecules that have got proper molecular orientation. Okay. So for all those molecules that are colliding with the collision frequency, not all of them have got the right molecular orientation. Let's say an example that I gave you, like you have got the sodium chloride. If the potassium is supposed to react to sodium chloride and then potassium is colliding with sodium, this reaction won't happen. Why? Because there is a wrong molecular orientation. So steric factor is telling us the fraction of those molecules that are colliding with the proper molecular orientation. Or we can also say steric factor is a probability that two molecules will collide with the right orientation. Okay? Collision with right orientation. So if we combine now Z with P, the collision frequency with the steric factor, we're going to get A. So A in this case will give us the number of collisions happening in a molecule per second with the right orientation. You've seen how I've put it. Collision frequency is the collisions per second. Steric factor is the collisions with the right orientation. So A is the number of collisions happening per second with the right molecular orientation. So now to put it all together, what are the factors that determine the effectiveness of a collision? Number one, the first factor is proper orientation. Proper molecular orientation. That's the first thing that should be met. Number two, there should be sufficient energy. Where is the energy? It's the activation energy that you can see. Okay? Enough energy. Enough energy. So if the energy is not enough, the reaction won't happen, even if the collisions are happening, because there's actually a mountain that you have to overcome. We call that as the activation energy barrier for a reaction to be able to happen. Number three, another thing that you need is the temperature. You can see the temperature is part of this equation. Okay, temperature. So the temperature should be high enough so that the collisions can happen at a faster rate and then the collisions will be able to happen. These are the main factors. And also the medium is also important. Medium in which the reaction is happening. Okay. For example, a solvent medium or a medium that contains the right pressure, it is very important. So those are the factors that are important for a reaction to be able to happen. Is there anyone that is having a question? Anyone that is behind? Anyone having a question? Okay. I hope we are okay. Please, if you are not, feel free to ask. Let's go to question 2. Question 2 is saying for a certain reaction, the value of Arrhenius factor. So if you multiply A, Z, and P, it gives you the Arrhenius factor. That A. So for a certain reaction, the value of the Arrhenius factor and activation energy have been given there. 4 times 10 to the power 13 collisions per second and 98.6 kilojoules per mole at 303. Calculate the rate constant if reaction is first order. So for you to be able to do that, you would just use the Arrhenius equation. Arrhenius equation K is equal to A. Remember I said ZP, but that ZP is equal to A multiplied by Euler's number to the power negative activation energy divided by RT. Okay, so that is it. So A, which is the Arrhenius factor, has been given 4 times 10 to the power 13 collisions per second. So 4 times 10 to the power 13. E is Euler's number, is 2.7. So I'll just write E because your calculator actually has got just E there. The activation energy, where is it, has been given as 98.6. Now please guys, use the activation energy in the right unit. The activation energy here has been given as in kilojoules, but you don't use kilojoules. You need to convert that to joules. Okay, So that's important. So what do you do? This is kilojoules per mole. Just multiply by 1,000, and then it's going to be in joules per mole. Therefore, this is 98.6 times 1,000 will give you 98,600. Okay, don't forget to attach a negative. Let me write this one properly. So this is a power. I'm going to write it like this. I'm going to write that 98,600. In the denominator, we have got R. R is the universal gas constant, and the universal gas constant is 8.3145. We are multiplying by the temperature. Temperature, please, should always be in Kelvin, and that is 303. Okay, and so we are going to follow it up like this. So this is 4 times 10 to the power 13 multiplied by Euler's number. So we'll just simplify 98, negative 98,600 divided by 8.3145 times 303. That is going to give us a negative 39.138. And then you just punch on your calculator. You just go where there is shift, and then you punch where there is a natural log on your calculator. If you punch that, it will show E on your calculator. Once it shows E, just write negative 39.138. Don't put a comma symbol for power, just write direct. Okay? And then the answer that you get, you now multiply by 4 times 10 to the power 13. If you do that, that is going to give you the value for K as 1.628 times 10 to the power negative 4. Remember, they said that this is a first order reaction. So the unit for the rate constant for a first order reaction is second to the power negative 1. How do we find the unit for K? Unit of K is given by molarity to the power 1 minus N multiplied by time to the power negative 1. N is the order. So since this is a first order, it will be molarity to the power 1 minus 1 and then time to the power negative 1. 1 minus 1 is a 0. So m to the power 0, the answer is 1. So it just remains time to the power negative 1. So time can be in anything. Okay, it can be hours, days, years, seconds, just like that. So for this one, okay, because they gave us second, that's the one we are dealing with. So that's why where there is t, I've put now second. So that's why I've written second to the power negative 1. Are we okay, guys? Is there anyone that is behind? Yes, Maureen. Your hand is up, Maureen. Okay, is there anyone else that has a question? Seems our friend can't be able to say. We are okay, we can proceed. Okay. Number 3 is saying, given a reaction A plus 2B producing 3C plus 2D and the rate of disappearance of B is that. So the rate of disappearance is supposed to be molar per second. And then it's saying calculate the rate of disappearance of A and then that. So what I want you to know this, guys, is this. When you are finding the rate of a reaction, right? The rate of a reaction, what you do is that you are going to get a change in concentration. So for the reactants, please know that when a reaction starts, reactants disappear, products appear. Okay? Because imagine when you are cooking in shima, what happens to the water? The water is going, the middle meal is going, you're having in shima. So water and middle meal, those are reactants. Shima is a product. So reactants disappear. So what you do is rate is given by change. So the change, in this case, we're going to start with A. So get the change in the concentration of A. I can either write dA or I can write delta A. It's the same. The triangle and D both means change. So we're going to say change in the concentration of A divided by the change in time. But remember, since A is on the reactant, attach a negative. And this should be equal to the change in the concentration of B divided by the change in time. I've also put a negative there. Sorry, just a moment. Sorry, guys. Something just happened with the network here. Can you see the screen now? Are you able to see now the screen? Thank you. So let me just say this again, what I was writing here. Okay. So when you are finding the rate of a reaction, the rate is given by you get a change in the concentration on the reactant. So you're going to say change in the concentration of A divided by the change in time. Rate is always change amount over time. Okay. Change in concentration of A over change in time. And this should be equal to the change in the concentration of B over the change in time. And it should also be equal to on the product the change in concentration of C over the change in time and the change in concentration of D over the change in time. Now after you write this, the next thing that you are going to do is now look at your balanced equation. For reactants, always attach a negative in front, all right? Because the reactants always disappear. In other words, the concentration on the reactants always decreases. So let's say, for example, for A, the concentration at the beginning was 20. After a certain time, the concentration is now 5. When you are finding the change in concentration, it's supposed to be final minus initial. So 5 minus 20 is giving us a negative 15. But the rate can't be negative. That's why we attach this negative in front so that it cancels with this negative. Rate is speed. You can't have negative speed. It's not possible. It's not velocity. Velocity, that negative also just tells us the direction. It's not like the number itself is negative. It's just the direction. Okay. And then another thing that you do is that for those numbers for those reactants or products that have got a coefficient will go in the denominator. For example, B has got a 2. So that 2 will go in the denominator. C has got a 3. The 3 will go in the denominator. D has got a 2. It will also go in the denominator. So this is how you find the rate. So for us to answer question A, we've been told that we want to. Yes, please, there's a question. Yes, Stefania. You can open your mic and speak if you have. You can't see the screen. Is it the case with everyone else? We can't see the screen? Is there anyone that can see the screen? Okay, so others are able to see, so you can just disconnect and then connect back if you can't see, right? And then you'll be able to see. Okay, so the question A is saying find the rate of disappearance of A. They've given us the rate of disappearance of B. Now, again, as I said, reactants always. So what I've written here is just one expression. Please take note of this. This is one expression that we can use to find the what? The rate. Another thing, if they've given you the rates, you can use another formula. You are going to say the rate will start with 1. So for reactants, remember reactants disappear. So the rate of disappearance of A is going to be equal to the rate of disappearance of B, and that is also going to be equal to the rate. Now we go to the product. The products appear. So it will be the rate of appearance of C, and that will be equal to the rate of appearance of D. But don't forget to divide by the coefficients. For B, it has got a 2, so divide by a 2. C, there is a 3, so divide by a 3. D, there is a 2, so divide by a 2. So these two expressions are important when you are finding rates. So therefore, to answer the first question, we want to find the rate of disappearance of A. We already know the rate of disappearance of B. So just say the rate of A is equal to the rate of B divided by 2. But remember, these rates for A and B is disappearance. So the rate of disappearance of B we've been given as 1 times 10 to the power negative 2. So you divide this value by 2. Let's see what we get. Okay. So of course it's going to be 2 into 1. That is a 0 0.5. So this is going to give us the rate of disappearance. So it's going to be 5 times 10 to the power negative 3 molar per second. Okay. And then I want to find B, the rate of appearance of C and D. So the rate for C will also use still B because that's the one we are given. I can also use A. So we will say the rate, you can get any two relationship as long as you know the rate for one, you can use it to find the rate for the other one. So let me use A since I already know. Or I can still use it. I can still use which one? Okay, I can use B. Or let me use A since it's simple. So we'll say the rate of A is equal to the rate of C. But remember C is divided by what? By 3. What is the rate of A? We've just calculated that 5 times 10 to the power negative 3. And that will be equal to the rate of C over 3. Therefore, all we do to find the rate of C, rate of C is going to be 3 multiplied by 5. That's a 15. Okay. So this is going to be 15. But if I write it in standard form, it's going to be 1.5 times 10 to the power negative 2 molar per second. And then to find now the rate of D, what you have to do is now compare any two again, okay, to find the rate of D. Let me write it on top. Okay. So again, I can use the same A. You can decide to use anything that you want, right? It's going to be still okay. So I'm going to bring it here. So that's question B. So we'll say the rate of A is equal to the rate of d over, remember d was divided by 2. Now another thing that I forgot when I was writing this rate, please don't forget again to attach a negative. Please don't forget that. Okay? Because these are the reactancy, it's disappearing. So you have to put that negative in front. But in this case, since we were already told that this is, look at this, I want you to understand language. If I just say rate of A, I'm attaching a negative because I don't know if it is rate of appearance or disappearance. So for the reactants, I attach a negative. But if I just say, if I said rate of disappearance, just the word disappear means that this number carries a negative. So I'll not attach any negative there. I hope you get the language, all right? So just by virtue of us saying this is the rate of disappearance, it means that in the formula where we're supposed to have, because supposed to be negative rate of A. But remember the rate of A was the rate of disappearance and it is 5 times 10 power negative 3. So there's a negative that is part of the formula, but there's a negative that is coming just from the word disappearance. So it will still up giving you a positive. And this should be equal to the rate of appearance of D divided by 2. Now these two multiply with a 5, that will give us a 10. So therefore the rate of disappearance of D, or of appearance of D, is going to be 2 times 5, that will give you a 10. So it will be 10 times 10 to the power negative 3, which will just be 1 times 10 to the power negative 2 molar per second. Okay, so that is how I answer this one. Have I lost anyone at any point? Is there anyone that's behind? Okay, so we can do now the next one, question 4. A reaction has a rate constant 0.051 per minute. Yes, please, there's a question. Maureen, you can open your mic, please. Mm-hmm. Okay, that's correct. So if you are comparing these two, you've seen, if you want to compare C and D, the rate of appearance of C over 3 is equal to the rate of appearance of D over 3. So if you want to find the rate of appearance of C, you can just get this 3 in the denominator and multiply on top here. So it becomes the rate of appearance of C is 3 over 2, the rate of appearance of D. Okay? Okay. Is that all right? Is there any other question? All right, good. So number 4, a reaction has a rate constant of 0.051 per minute. We can also write this as 0.051 minute to the power negative 1. It's the same thing. Okay. If we begin with 0.1 molar concentration of a reaction, what is the order of the reaction? Now, you just looking at the unit of the rate constant, unit of K. Look at the unit. It is per minute. Per minute means minute to the power negative 1. Okay. So if you want to find now the order of the reaction, remember the unit of K is given by molarity to the power 1 minus n, and then time to the power negative 1. So this general formula for the unit for K should be equal to this one, minute to the power negative 1. But we don't have any molarity here. It means that molarity is raised to the power 0. Okay? Because molarity raised to the power 0, the answer is 1. This minute to the power negative 1 is the same as this time to the power negative 1. So it means that the powers of m should be equal. So 1 minus n should be equal to 0. Take n the other side. So n is equal to 1. So that tells you that this is a first order because n is equal to 1. Hope I have not lost anyone. Have I lost anyone? Please, if you are behind, feel free to ask, okay? Okay. The next question is saying, what concentration of the reactant will be left after 3 hours? Okay. What concentration of the reactant will be left after 3 hours? Now remember, we have got the rate constant and we have the initial concentration. So we can use two methods. I'll have method 1 and then I'll put method 2 this side. So for method 1, we'll just start with our initial concentration. Okay. So the concentration of A at the beginning is, that's the initial concentration, is 0.10 molar. No, so what is half-life? Half-life is defined as the time it takes for something to change by half, for the concentration to drop by half, isn't it? That's what we call half-life. So if we'll be dropping the concentration of this guy, okay, let me use the first one. We'll use the formula so that it can be way easier. Okay. What is the concentration after 3 hours? Remember, this is the first order reaction, so you need to know the integrated rate law for a first order reaction. And how do you find that? It's then for first order reaction, natural log of the final concentration is equal to natural log of the initial concentration and then minus kT. Or we could have said natural log of the final concentration is equal to negative kT plus natural log of the initial concentration. It's the same thing. The final concentration is what we're trying to look for, so we'll say natural log of the final concentration. This will be equal to natural log of the initial concentration. The initial concentration is 0.1. And then minus k, you can say k is 0.0051. The time, where is the time? We've been told after 3 hours. But remember, this guy is in per minute. So you also need to convert the time to minutes. So how many minutes are in 3 hours? So the time is 3 hours times 60. And that is going to give us 180 minutes. So that's the one we punch here. So this will give us natural log of final concentration is equal to natural log of 0.1 is going to give us a negative 2.3026. 0.0051 times 180, that will give us 0.918. And then you subtract those. So we're going to have natural log of the final concentration being equal to negative 3.2206. But remember, natural log is a log in base E. Okay? Natural log is a log in base E. So this guy, if let me write it, this is the same as log in base E of the final concentration, and that will be equal to negative 3.2206. You need to convert now a logarithm to exponential function. How do you do that? Logarithm to exponential, this base, so this will become the A final concentration will be equal to this number that is here, AF. You get the base, which is e. The number that is after the equal sign is the power, negative 3.2206. So the way you convert logarithms to exponential function is you say e to the power this number is equal to this number that is here. So e to the power negative 3.2206 is equal to a fine. Okay, so that is how you convert. So now you just punch that on your calculator. Okay, so you just punch this on your calculator. It's going to give you 0.0398 molar. The way we convert logarithms, when you have got log of x in base x, let's say of 2, is equal to 4. Let's say convert this guy to an exponential function. It is x to the power 4 is equal to 2. That's how we convert x to the power 4 is equal to 2. So it means that 2 is equal to x to the power 4, and then you can solve for x. Is that okay? Is it okay on converting the base, the log? Yes. Okay, so what we are saying is this, huh? If you have got log in base e of x is equal to 2, this base, the base will be raised to this number, and that will be equal to whatsoever number is here. So it will be e to the power 2, and that will be equal to x. It is always this number that is here, which is the base, raised to the power, the end number. It will be equal to this number that is on the middle. Okay. And then the next question is saying calculate half-life. Now the formula that I wanted to use, so method 2, will not use it here because we don't know yet the half-life. I'm going to show it on another question, another method that we can use. But we can go what will be the half-life. Now this is a first order reaction. For a first order reaction, half-life half-life is given by natural log of 2. Natural log of 2 over k. So this will be natural log of 2. K, the rate constant, is 0.0051. So just punch that on your calculator. It will give you 135.88. Now remember, time for this question is in minutes. So that will be the half-life. That's how you find it. And then this is saying a reaction of second order with respect to a reactant. How will the rate of the reaction be affected if the concentration of this reaction is doubled? Okay, you get that. A reaction of second order with respect to reactant. Let's say you have got A going into B, and you've been told that this reaction is second order in respect to reactant. So it means that how do you find the rate? The rate is going to be equal to K concentration of A raised to the power 2. Okay, like that. How will the rate of the reaction be affected if the concentration of this reactant is doubled? So now look at this. What will happen if the concentration is doubled? So the rate is going to be equal to K. The concentration is doubled. So you can see the rate is going to increase by 4. So therefore, if concentration is doubled, rate increases by a factor of 4. By a factor of 4. Or we can say the rate quadruples. Is this okay, guys? Are we okay? Is that okay? Okay. Please feel. Let me see if people are understanding. Let me see reactions. Please just react with any emoji on your screen. I see if people are getting what we are talking about. Michelle, I can't get what you're saying. You can say that again. Okay, just give me a second. I just do something. Seems it's if you are able to type the question because I can't get you, please kindly type if it's not too long. That's okay. Or yeah, if you can if you can type, please type it. Or let me just listen to it because the it's like my headsets can't get you if you are speaking. So I can use just give me a second. I've seen someone that has typed a question. Okay, so someone is saying, how is the concentration 2? Because 2 is the order, not concentration. So the 2, remember the question is saying, how will the rate of the reaction be affected if the concentration of this reaction is doubled? So that double is how the 2 has come about. Is it okay, Vualia? Excellent. And then, yeah, Michelle, you can now open your mic and ask. Okay, question C. Yeah. Okay, so it's just an equation that you have to know for if the half reactions, sorry, not half reaction, but half life of each reaction you have to know. You need to know for a zero order, for a first order, and also a second order, the formula for half life. So the first thing that you need to know is the integrated rate law for each one of these. Maybe let me just write them so that we get the sense out of them and then we'll be able to apply. Okay. So we are going to have zero order here, and then first order, and then second order. We are going to have their integrated rate law, and then we are going to also have the half-life at this point. So for a zero order reaction, what you need to know for this one is the integrated rate law for a zero order is the final concentration is equal to negative the initial concentration, and then you say, actually not this negative is not supposed to be like this, supposed to negative kt, and then plus the initial concentration. The first order reaction, it's similar to this one. The only difference is you put natural log. So natural log of the final concentration is equal to negative Kt plus natural log of the initial concentration. Okay, you see how it is? And then now when you go to the second order, the only thing that changes is that now it becomes like a fraction. But everything else is a bit similar. And another thing is that the gradient is going to be positive. So it is 1 over final concentration is equal to, this is positive Kt instead of negative, and plus 1 over the initial concentration. So you need to know these rate laws for these guys here. Okay. And then the next thing now to know is the half-life equations for each one of them. Just give me a second. Okay, thank you so much. So when we go to the half-life, starting with the zero order reaction, half-life for a zero order reaction is given by T half is equal to the initial concentration divided by 2K. When you come to a first order reaction, the half-life is natural log of 2 over K. And then for a second order reaction, the half-life is going to be 1 divided by K multiplied by the initial concentration. So please, you need to know these equations because these are the ones that you're going to be using when they ask you. So because we are given a first order, that's why we picked the half-life to be half and natural log of 2 over K. Does that make sense now? Excellent. So question 5 is our next question. Nitrogen pentoxide decomposes according to the equation that we can see there. The reaction is first order and was allowed to proceed at let me see the temperature there. So at 40 degrees Celsius. Next question is calculate the rate constant. Include units with your answer. Okay. Rate constant. So how would you find the rate constant if you've been given? You can see we've been given the concentrations and the time for each concentration. So what you can do for this one is you can use one principle that we gave earlier. We can say if we use let's say we use the integrated rate law. So for question A, remember they've said this is a first order reaction. So it's natural log of the final concentration is equal to negative kT plus natural log of the initial concentration. Okay. So you can choose two data points, any two data points, but remember you need to have the initial. So let's say if we pick the initial concentration is the O is the one at time is equal to 0. You can say that's 0.4. And then get any other concentration that you are going to call the final concentration. In this case, let me pick 0.289. You can just pick any. And this is at time is equal to, you can see that's at 20. The unit for the time is minutes. Okay. And then we'll be able to use these two. So we'll say natural log, the final concentration, in this case, is the one that we've said there, 0.289. And that is going to be equal to negative k, we don't know, the time is 20, plus natural log, the initial concentration is 0.4. Okay. So if you punch natural log of 0.289, that gives you negative 1.241, and that will be equal to negative 20k. Natural log of 0.4, that is going to give us, let me punch that, natural log of zero point 0.4, it's a negative 0.91629. I'm going to take 20k, the other side becomes positive, and that will be equal to, I'll take this number the other side, so it will become positive, so it will be plus that number. So the answer that is given me is negative 2.15. Let me punch this again because it doesn't seem to be correct. So if I get natural log of 0.28, just the way it is, I take it the other side, is going to become, okay, let me just pick it from this point. I wanted to write it direct from this point. So negative 0.1916, if this term goes the other side, it will become positive 1.241. So it's going to give us 0.3247. And it's now this one we are going to divide by 20. Therefore, k is going to be 0.01625. Remember, this is a first order reaction. The unit for k is always to the power negative 1. Looking at whatsoever unit of time. If it was second, it would be second to the power negative 1. Is this okay, guys? If it's okay, please react. If you are having any question, be free to ask. People are not reacting. I need to see reactions. Okay. B is saying, what will be the concentration after 100 minutes? So again, we'll use the same equation. Natural log of the final concentration is equal to negative kT plus natural log of the initial concentration. So this will be natural log of the final concentration is equal to, so we'll substitute negative, remember the k we found 0.289, 0.1625. The time, this is after 100, plus natural log. The initial concentration is 0.4. So this will give us natural log of the final concentration is equal to, just punch guys direct, negative 0.01625 times 100 plus natural log of 0.4. That will give you negative 2.541. Again, remember a natural log is a log in base e, and then write a f, that is equal to negative 2.541. Express this in exponential form, so it means that the final concentration is going to be equal to e raised to the power negative 2.541. Therefore, the final concentration after 100 minutes is going to be 0.078 molar. The last part of the question was saying, calculate the initial rate of the reaction. So how would you find the initial rate? You can sketch a graph if you want, because the way you are seeing this one, let me just approximate it for you so that you just get a sense out of it. Huh? So the y-axis has got concentration, the x-axis has time. So for time, we are going all the way up to 8. So let's say this is 20, this is 60. No, before 60 we have a 40. This is 60 and then 80 somewhere there. And then going up, you can see we have 0 0.4, 0 0.2, 0 0.1. So it can be moving like that. Let's say this is 0 0.1, this is 0 0.2, 0 0.3, and then at the end we have got 0 0.4. So the first coordinate is 0 0.4, comma 0. That's on top. The next one is 0.289, comma 20. 28 is going to be somewhere near 0.3. The next one is 0.20, comma 40. This one is very near to 0.2. The next one is 0.15. Like this is somewhere on the middle between 0.1 and 0.2, comma 60. The next one is 0.1, comma 8, like, yeah, something like that. It's supposed to be a straight line. Now remember, for a first order reaction, its natural log, the integrated rate law, final concentration is equal to negative kT plus natural log of the initial concentration. This equation is in the form y is equal to mx plus c. So you can see y is correlating to natural log of f. M, which is the gradient, is correlating with negative k. And then you have got time, which is correlating to x, and then c correlating to the initial concentration. So you can actually calculate the value of k, like the question they asked us, what calculate the rate constant k. You could have used the graph. What you just do is determine the gradient. Just get any 2 points. Find the gradient. How do you find gradient? Gradient is change in y over change in x. Once you find the gradient, let's say you find 2. So meaning that k will be negative 2 because gradient is equal to negative k. But question C is asking us to calculate the initial rate, not any one of these. How do you find rate? Remember, this is a first order reaction. Rate is given by K multiplied by the concentration. First order is be raised to the power 1. Now we've already determined K and we found 0.01625. What is the initial concentration? It's 0.4. So therefore our initial rate is going to be 0.0065. Concentration is in molar, time is in minutes. That is how you find this one. Next part of the question, question 6. Are we okay with question 5? Reactions, please, or questions? Okay, good. The following results were obtained in experiment designed to study the rate reaction of the reaction X plus 2y is producing to Z. Determine the order of the reaction with respect to each of the reactants and write the rate equation for the reaction. Now, first thing that I want you to identify is this. When you are when you want to determine the order, you need to basically know what power we're going to raise x to and y. When you're finding rate is given by k. You get a first reactant, which is x. We don't know what the power is going to be. Let's say it's n. You get a second reactant, which is y. You don't know the power. Maybe it's m. Please, you don't get the numbers in front. Okay, not for this one, unless if you are dealing with other problems with the equations, which we call the molecular equations, or the ones that have got molecularity. So in this case, you can use two ways. I can find the value of n and m by just looking at these constants or these numbers. If you look at compare equation 2 and equation 3, can you see that for equation 2 and equation 2, this one is constant, right? So it will cancel. Look at what happened to the initial concentration. We moved from 0.05 to 0.1. So what happened to the concentration? It doubled. Okay. And remember, that is x. So x has doubled. Now y is the same, so y will remain the constant. And then look at what happened to the rate of disappearance. Okay. Rate of disappearance. So we moved from 6 to 1.2. Now it will be hard for you to be able to tell, but just say how many times does 6.0 times 10 to the power negative 3 go into 1.2 times 10 to the power negative 2? So this is basically how many times does 6 go into. So what you say is 1.2 times 10 to the power negative 2 divided by 6 times 10 to the power negative 3. 10 to the power negative 3 can go into 10 to the power negative 2 the 10 times. 10 times 1.2, that will be 12. 6 into 12 is 2. So you see what has happened? So the rate, the initial concentration when it is doubled, the initial rate is also doubled. So this means that this is the first order with respect to x. But for the sake of calculation, we are supposed to show the calculation here. Okay. So let's just show the calculation. So we're going to get equation 2 and equation 3. We'll be substituting in here. I'm going to get equation 2 over equation 1. So equation 2, the rate, oh, sorry, the equation 3 divided by equation 2. Well, remember, we're getting two equations at a time. And I've chosen to get these two because y will cancel out. So equation 3 the rate is 1.2 times 10 to the power negative 2. That is going to be equal to, I'll write K. I'm just copying this one. And then X. But remember the initial concentration for X, that is 0.1. And that will be raised to the power X. And then for Y, the initial concentration is also 0.1. That will be raised to the power Y. And then for equation 2, the rate, you can see is this one, 6.0 times 10 to the power negative 3. That will be equal to K. Why did I change these things? This is supposed to be raised to the power N and M. So for equation 2, where there is X, we are getting the concentration for X, 0.05. And then where there is Y, we are getting 0.1. So you see that this part will cancel with this part. And we already say that 6.0 times 10 to the power negative 3 into 1.2 times 10 to the power negative 2, that will give us a 2. This K will cancel with this K. 0.05 into 0.1, that's a 2. So this tells us that 2 is the same as 2 to the power 1. So N is going to be equal to 1. And then we now solve for M. Get any one equation among two equations or two experiments such that X will be able to cancel out so that Y remains. So we'll get the first two because X will be able to cancel. So the rate for the last one is 6.0 by 10 to the power negative 3. That will be equal to K. The concentration of X, you can see that's 0.5. Sorry, 0.05 raised to the power N. Concentration of Y, 0.1. This is raised to the power M. The first equation, the rate is there. 3.0 by 10 to the power negative 3. That will be equal to K. Concentration of X, 0.05 raised to the power N. Concentration of Y, 0.05 raised to the power M. So K cancels with K. 0.05 also cancels with 0.05. 3 into 6, that's a 2. 0.05 into 0.1, that's also a 2. So you can see that this is still M to the is equal to 1. The question was saying, determine the order of the reaction with respect to each of the reactants. So we are saying the reaction is first order to N to X and first order to Y, and write the rate law for the reaction. So therefore the rate law, rate is going to be equal to K, X raised to the power 1 and Y raised to the power 1. Okay, so that's how you answer that one. And then B was saying calculate the value of the rate constant. To find the value of the rate constant, you can use any one of the equations. So if we get equation 1, rate is going to be equal to, remember, K, X, Y. You get the rate for equation 1 is 3 times 10 to the power negative 3. And then the concentration is both 0.05. 3.0 times 10 to the power negative 3 is equal to K, 0.05 times 0.05. Just divide both sides by 0.05 times 0.05. That will give you K being equal to 1.2. Because it's the first order reaction. Is this a first order? No, it's a second order because you have got two things. The unit for second order reaction, remember it's m 1 minus n times to the power negative 1. Where there is n, put 2. So that will be m 1 minus 2 negative 1 and then time to the power negative 1. So the unit will be m to the power negative 1. But remember time is in, what unit are we using? It's seconds. So it will be second to the power negative 1. And then the last question, if another experiment is attempted with x and y, both 0.02 molar, what would be the initial rate? So C, remember both with a 0.02. Okay, calculate the initial rate. So the initial rate would be k, x, and then y. Okay. So this is going to be, remember k is 1.2, and then we've been told x, both have got a concentration of 0.02. So you multiply, where there is x you put 0.02, where there is y also 0.02. So that will give us 4.8 times 10 to the power negative 4. This is the rate. It is molar per second, the unit. So that is it. We are just remaining with 3 questions. For these ones, we'll answer them in the next discussion. Thank you so much for today. Have a blessed evening.